Yeah. Now that we have looked at the measures of central tendency, which talk about the middleness in the data, the spread talks about the distribution of the data. And of course, though there are many measures of spread that are available in the statistics space, the most common thing industry uses is the standard deviation, which is nothing but as a simple measure we are talking of the spread in the data. Is because see, average always talks about something in the middle, but how are the other elements? Are they very close to the center, or are they very much away from the center? So that is what is being understood by the measure of spread, right? So talks about either the dispersion or variability or the scatter in the data. And sometimes we do try finding out the deviation from the mean. Most commonly, standard deviation as a definition is nothing but average deviation from the mean. Whereas sometimes I may be interested in finding out the deviation with respect to any other value also. Sometimes I may do it with respect to median. Sometimes I may do it with respect to zero. So at the end, the common definition is any deviation from a particular point. So there are so many terms which are generally used. Of course, the standard deviation is the very common one. It is used just like the way mean is used as a measure of central tendency, right? Mean, one thing to remember, there are two different symbols for the mean, mu and x bar. X bar is always associated with the sample mean. It's a very common term to use. You should not use these two things interchangeably, right? When you are using x bar, it means the mean of a sample of data. But when we are using mu, it is the mean of the population. So to a large extent, we always work with the samples only. But when we are estimating, we estimate the population parameter. So we should use the mu and x bar accordingly. The same thing holds true with the standard deviation also. When I talk about population standard deviation, I use sigma. Whereas when we talk about sample standard deviation, S is being used. So the difference of these two should be, because sometimes you see in the books also saying S is a good estimator of sigma, or S squared is a good estimator of sigma squared. So because whenever you are estimating something, you estimate the population value. But the data is always specific to a sample. So the whole world of statistics runs like you use the samples data to estimate the population stuff, right? So the differentiation between these terms need to be comfortable with. And population is the complete data. Let's say you are having the whole list of policies, probably some, I mean, there is nothing beyond that. That is what we call as the population. But whenever we work, we don't access the whole data in the world, right? When I have to make some conclusion, let's say elections, right? If I go to each and every voter and find out to whom they have voted, then it is the population. But I go only to some set of people and take their data. Even when you are talking of insurance policies or probably estimating the mortality of a particular person, whatever it is, the probability of accidents, whatever it is, I will not take all the accidents in the country, and I cannot get the whole data, right? Probably some accidents don't get reported, lot of things may happen. So I may not get the whole data. So whatever I work on is only some portion of the whole data. That is what we call as a sample. So any calculations we do, generally, we work on the sample. Even in the exam, if he gives a data, he hardly gives some 50, 60, 100 element. Right? Using that 100, he asks you to generalize. So that is where we are actually using statistics itself. I am using a sample to do something about the population. Right? So that's where even in terms of terms also, S is something I use for sample standard deviation, and sigma is something which I use for population standard deviation. So we'll look at the measures of these two. And along with that, there are a couple of other dispersion measures also. One is called as the moments, right? We'll look at the formulas and all associated with each of them. The moments is a very general term. Even the mean and the variance are also special cases of moments. We'll see that. Then there is a mechanism called range. Range is easiest to find out, which is nothing but highest value minus lowest value. So that's the reason it is not used more extensively, because the form, it's very simple and only two values are considered. Even though my sample will have 50 values, range only considers two values, highest value and lowest value. And if the highest is an outlier and the lowest is an outlier, right, the difference looks very, very high. So it says the data is completely dispersed, completely scattered. Probably if I remove that one outlier, probably the data looks more concentrated in a specific area. So that's where range is not generally used heavily. And of course, we'll look at the interquartile. So these four are the ones which are typically considered as the measures of dispersion as far as our syllabus is concerned. Now, how do I look at each one of them? When we say standard deviation, we cannot compute the standard deviation directly. The first thing we compute always is the variance. And from the variance, we will compute the standard deviation. Nothing but the square root of the variance. Square root of the variance is nothing but the standard deviation. Now, what are we talking of variance? If I say x bar is my mean of the data, whatever data I have taken, x bar is the mean of that. Now, each value, you subtract the mean, which means each value, how much is it away from the mean? How much is it away from the mean? So that, what we are saying is, this may be positive or negative, right? So we are, when we are talking of deviation, we will only talk about a positive quantity. So that's where, to bring out a positive quantity, we do a squaring of that. So this is the deviation, square of the deviation of each value from the mean. And for this, I will take the average. And average, here when I am doing for the sample, I will divide it by n minus 1 and not by n. I add up all these things. And so the symbols wise, sigma is a notation for adding up. I add up for each number x minus x bar whole square and divide it by n minus 1 if the question is relating to sample standard deviation. For example, let me just take a simple example. 1, 2, 3, 4, 5 are my numbers. Mean x bar is 3. Right? 1 plus 2 plus 3 plus 4 plus 5 by 3. X bar is 3. Now when I am finding out my variance, each value I subtract from the mean, square it. Each value, mean, square it. Each value from the mean, square it. So each observation, you subtract it from the mean and you square it. That is the sigma x minus x bar whole square. So this you divide by n minus 1. So what is this? 2 squared 4, 5, 6, 10. 10 you divide by 4. Because there are 5 elements, we are dividing it by n minus 1. Okay, we'll decide why n minus 1, why not n. Probably there is one exclusive chapter at a slightly later point when we are doing estimators. See, the simple point is n minus 1. See, because this is a sample, right? Simple way, probably in simple terms, if I have to put it, we are always working on a sample. We know the sample mean x bar. If I know the sample mean x bar, let's say I am talking about my total data and 5 elements, right? Now, if I know the 4 elements, some 4 elements, the fifth element, fifth number should be in relation with x bar, right? Let's say my x bar is 3. If I know 4 numbers, 1, 2, 3, 4, the fifth number cannot be a random number. If 1, 2, 3, 4 could be random numbers, but the fifth number actually should be an adjusting number with respect to x bar. 1, 2, 3, 4. Okay, average is still 3. So if the average is 3, the fifth number should be 5. Then only the average will be 3. So which means the actual fifth number in my series is not a free number. It is based on x bar. So actual free numbers are only 4. That is the reason we divide them by n minus 1, because one number cannot deviate. So only 4 numbers are n minus 1 numbers that typically deviate. That is a conceptual way of presenting it. But of course, there is a mathematical way also. When we typically look at estimators, probably in chapter 9 or 10, then we'll discuss about why dividing by n is not a good estimator, but dividing by n minus 1 is a good estimator of population variance. Right? So for the time being, you can very well remember, if the question is being given as sample variance, you do a division by n minus 1 itself. If the question talks about population variance, you divide by n only. So that's where in the question always you will see, find the sample standard deviation. It will be very clear. If I am saying, because for the mean, there is no difference. For computation of the mean, whether it is the sample mean or population mean, sum of the numbers by total number of numbers. But once the mean is in place, one of my values is getting constrained. That's the reason for computation of my standard deviations and variances, I will always use n minus 1 and not n. So for the population variance or for a sample variance computation, we are using this kind of a formula. So in this case, 10 by 4, population variance becomes 2.5. And standard deviation is nothing but square root of 2.5. Right? And from probably even from your calculators, if you are using any of your scientific calculators, even without doing this much of calculation, just with a basic data entry itself, you can get the values of your mean, standard deviation. Any scientific calculator can directly give you the values of your mean and standard deviations directly. You don't need to do this entire process. You just need to do a data entry. It will give you the values for your mean and standard deviations, especially your scientific calculators. It will also give correlations. There are a couple of things which a normal calculator will directly give also. So probably once both of you have your calculators, we can do one or two sample problems using the calculator also. Right? Then, yeah. So dividing by n minus 1 rather than n, that's the one of the major things that we need to look at. So if you look at this, this is the typical formula for population variance. Every x minus x bar whole square divided by n minus 1. Now, typically people write this in a slightly different way also. If you look at it, I can expand this xi minus x bar whole square. It becomes what? Xi squared plus x bar squared minus 2 x bar into sigma xi. Or probably this becomes sigma xi squared. So sigma xi squared. So a minus b whole squared. Sigma xi squared plus x bar squared, or probably sigma x bar squared, because sigma is there before all. Sigma is there before all the terms. It's a summation. Summation of all the numbers. X bar is a constant. Because it is added so many times. See, it is like, look at it like this. Instead of X bar, you think of it as X1 minus X bar squared plus X2 minus X bar squared. Probably in simplicity, if you want to look at this formula, this is nothing but X1 minus X bar squared plus X2 minus X bar squared. This is what is the meaning of that sigma. So X bar squared is added so many times, right? So what is it happening if I have to look at it? X1 squared plus X bar squared minus 2X bar X1, the first one. So X2 squared plus X bar squared minus 2X X bar X2. Like this it is going. Now if I simplify it, X1 squared plus X2 squared plus X3 squared plus so on. What is it becoming? Plus sigma Xi squared. Plus n into X bar squared. Right? And what about this? I will take out 2X bar common for the remaining stuff. It is becoming X1 plus X2 plus X3, which is nothing but X1 plus X2 plus X3 plus so on, which is sigma Xi. Right? Now, so I can very well write the X minus X bar. So I can very well write this as Xi squared, sigma Xi squared minus, now this sigma Xi. If I take the average of this, see now we need this as divided by n. Right? This is the summation. Summation, and we are saying average. Divide by n or n minus 1. So when I am dividing typically by n, you assume that I am dividing by n. Now what is happening? This entire thing, if I divide by n, it actually becomes sigma Xi squared by n plus this, what will it become? N into X bar squared by n. So it becomes X bar squared minus 2X bar sigma Xi by n. That is also X bar. So 2X bar squared it becomes. Now it is simply becoming sigma Xi squared by n minus X bar squared. Even this, this will come out for a population variance if I am dividing by n. If I am dividing by n minus 1, this logic cannot come out. Right? So the most common thing here is the simplified formula is you take it as Xi minus X bar whole squared divided by n minus 1. And if I go with the population, frequency distribution, right, using the same formula. Now we have used the sigma Xi squared minus n into X bar squared. The same logic if you are using it here, instead of Xi squared, here we are taking it as the frequency multiplied by because when there is a frequency distribution, we are taking the frequency multiplied by the corresponding values. Because the value is not the value for us in a frequency distribution. Value is always the multiplication by its corresponding frequency. Right? So, the best thing is when you are looking at the numerical itself. See, when you are typically looking at a simple frequency distribution like this. A simple frequency distribution like let's say 0 claim, 1 claim, 2 claims. There are 5, 8, 12. So your X bar in this case is 5 into 0 plus 1 into 8 plus 2 into 12. 24 plus 8, 32 divided by 12 plus 8, 20 plus 5, 25 is your x bar. Right? Now what you can do? 0 minus x bar. Each observation you are subtracting. So 0 minus x bar squared, whatever that x bar comes, that 32 by 25, plus this you have to multiply by the weighted average, 5. Similarly, 1 minus x bar squared, you are multiplying it by 8, plus 2 minus x bar squared, you are multiplying it by 12. Divide this entire thing by 12 plus 8 plus 5, 25. This is what is giving you in case of your frequency distribution. So depending on whether he is giving you a raw data or he is giving you a frequency distribution, you can try finding out your variance and the standard deviations for the data. Fine. Now, the next thing that comes in this context is the moments. Moments is nothing but, instead of mean, see in our standard deviation or variance formula, what did we say? Sigma xi minus x bar square. This is what we have done. Now when we say moment, it's a very generalized form of this. So all we are saying is sigma xi minus some a or some alpha. Instead of mean, you take it around anything. The deviation, see, standard deviation is a special definition saying deviation about the mean. Now here we are saying deviation about any number. Deviation about any number. So x bar minus alpha, using this formula, x bar minus alpha, and to the power some k. Why only square? Square is again a second moment. Typically every data is characterized by 3 or 4 moments. So to the power 1, power 2, power 3, power 4. Each 4 of them explain a different characteristic of the data. When we talk about power 1, the first power, typically associated with a mean. Mean is a first degree kind of an expression. When we take square, generally associated with variance in the data. When we take cube, we'll see the next section, it is associated with the skewness in the data. When we take 4, it is associated with another characteristic called kurtosis. We don't deal with it too much here. But when we take 4, there is another attribute of the data called kurtosis or the peakedness in the data. So the 4 moments statistically which describe the data from 4 different perspectives. So the generalized talk about a moment is xi minus some alpha to the power some k. K could be 1, 2, 3, 4. Alpha could be either the mean or any other number also. So if I put alpha equal to 0, and k equal to 1, it is nothing but the mean. Right? Sigma xi. Of course, by n is there. Right? Here also we have by n. So sigma xi by n is nothing but your mean, x bar. So these are all derived from the one general formula itself. Whether it is mean or variance. In variance what happens? Alpha if I put x bar. In place of alpha if I put x bar. And in place of k I put 2. It becomes the variance. Right? So that is how people compute the formulas for the various attributes of the data. Moments is like a kth order. 1, 2, 3, 4. Kth order thing. So sometimes in the exam what could happen is, he can ask you, find the third moment about the origin. Origin means 0 here. So take alpha equal to 0. Right? So if I say, just I'll give one example, 1, 2, 3, 4, 5. Data is this. Now he says, find the third moment about the origin. How do I find? What does it mean? Third moment about the origin means sigma. 5 data is there. So 1 by 5. Xi. Okay. Xi minus alpha 0. Because he is asking about origin. Minus 0 whole cube. This is what I have to find out. Sigma xi cube divided by 5. So it is nothing but 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube. The cubes of those first 5 numbers divided by 5. That is what will give me the third moment about the origin. Now if he says find the third moment about the mean, you are finding out mean as 3 for that data. So in place of alpha put 3 and do this calculation. So the third moment about the mean is nothing but skewness, which we will see in the next section. But the third moment about the mean, which is xi minus x bar cube, is what is a measure of skewness of the data. Right? Either the symmetric nature or skewed behavior in the data. Of course, next section is focusing more on that aspect itself. But that is how the moments will typically be used for making some of our calculations. Right? Now, of course, range is something which we have already discussed. The third mechanism of finding the dispersion in the data. The range is one of those methods, which is nothing but the difference between the largest and the smallest observations in the data. Maximum value minus minimum value in the data. So, because it does not take all the values, but if you see standard deviation, it considers all the values. It found x bar is found through all the values. Every value I am taking minus x bar and doing a square. So all values are involved in the calculation. Whereas when it comes to range, only two values are involved in the calculation, the highest value and the lowest value. That's one of the prime reasons the range is not a good measure. And if there are some extreme values, the highest and the lowest, if there are outliers in the data, probably the range looks very, very high. See, for us the interpretation is, if the standard deviation is high, then it means there is a lot of dispersion in the data. The data is fully scattered. Now if the range is high, then also I have to say the same. The data is fully scattered. Now only one value scattered, rest all are in the middle itself. Still it will say the data is scattered. So that's the reason range is always not a trustworthy kind of a tool for measuring your dispersion in the data. Then, yeah, this is a slightly better value. Interquartile range. Now for this, the data is broken into quarters. Right? Data is broken down into quarters. The way it is broken down is, let's say I take some data. I take some data. Okay, let me do it on a random basis. Okay, let's say I have some 20 data. So if someone asks me for this 20 data, find out the interquartile range. The simple thing I will do on this is, first find out what are the quartile values. What is the quartile for me? Quartile is just like a median. Median divides my data into two halves. Quartiles divide my data into 4 equal parts. Right? So in the median we have written a formula saying n plus 1 by 2th element in the data is the median. Right? If there are 20 elements here, first arrange them in the ascending or in the descending order. So let's say I arrange them in the ascending order. I arrange them in the ascending order. Right? I need n plus 1 by Q2 is nothing but second quartile, which is nothing but the median itself. Q2 will be the same as the median itself. And I need the n plus 1 by 2th element, which is the 20 plus 1, 21 by 2, 10.5 element. Okay, what is the 10.5? 10th element is this. 11th element is this. So 10.5 is something in the middle between these two. So the median or the second quartile for me is 41.5. Right? That this distance, okay, the value should be between 41 and 42 in the middle. So that is nothing but 41.5. Now the same way I will find out the quartile 1 and quartile 2s also. Quartile 3s also. The quartile 1 is nothing but n plus 1 by 4th element. Whatever splits the data into a quartile. 25%, just like the definition of median says, half of the value should be left side of the median, should be below the median, half of them should be above the median. Here also what we will say is, for a quartile 1, 25% of the value should be below it, 75% of the value should be above it. For Q3, 75% of the value should be below it, 25% of the value should be above it. Or the simple way to find out from a formula standpoint is, either I find out n plus 1 by 4th element for Q1 and 3 into n plus 1 by 4th element for Q3. And the same 2 into n plus 1 by 4 for Q2. 2 into n plus 1 by 4 is nothing but n plus 1 by 2. So that is the same formula which is being used for Q1, Q3, Q2 also. Now in this case, n plus 1 by 4, 20 plus 1, 21 by 4th element. 21 by 4 is 5.25 element. Right? This is where you have to be slightly comfortable. I need 5.25th element. Right? Okay, this is 5, this is 5, this is 6. I need 5.25. So typically the way you work out is, between these two, take it in such a way that it is 25% away from this one, because 0.25, 25% away from this one and 75% away from this one. Or the simple logic for you is difference. So take the 6th and the 5th, the difference being 32 minus 31 into 0.25. Whatever is the excess you want, you multiply it by 0.25. That you add up to your previous value. So 32 minus 31, 1. 1 into 0.25, 0.25. You add up your 0.25 to the 5th element, which is making it 31.25. So the median for me is 31.25 here. The quartile 1 is 31.25. The same way you can do for quartile 3. 3 into n plus 1 by 4th element. N plus 1 is 21. 21 into 3, 63. 63 by 4, 15.75 element. 15 is 43. 16 is 44. 15.75. So all you do is difference between 44 and 43. 1 into 0.75. 0.75. You add that 0.75 to the 15th element, which is making it 43.75. So 43.75 happens to be the third quartile. 31.25 happens to be the first quartile in this. Now, using this data, I can find out the interquartile range, which is nothing but Q3 minus Q1. The two quartiles, Q1 and Q3, I just take the difference between the Q3 and Q1, and that is what I call as the interquartile range. Now, the higher is this interquartile range, the higher we say that the data is dispersed. So this is a slightly better mechanism. The reason being, it is just not depending on only one outlier, one extreme value. There is also a range. That's the reason we are just subtracting two values. But we are not subtracting two extreme values. We are subtracting a 75% and 25% value. Right? If that is very much dispersed, then I can directly say with a lot of confidence that my data is having too much of dispersion in it. So that is how the interquartile range is being used, right? So we can find out the Q1, we can find out the Q3, and sometimes the Q1 is nothing but 25th percentile because we want 25% of the values below it. Q2 median is called as 50th percentile, and Q3 is called as the 75th percentile also, because percentile is nothing but that percentage of values are below it. That is the definition of a percentile for us. When we say 60 percentile, it is nothing but 60% of the values are below that particular value. Right? So, whenever we have 0.75, 0.25 kind of stuff, whatever the difference and which we are multiplying it, that process is typically called as interpolation for us. And just like the way we used the cumulative frequency distribution curve to find out the median, we can do it even for the quartiles. A curve, let's say this is how the cumulative frequency curve is coming, right? The 25 percentile value, okay, this is the 25, this is the Q1, 25th, right? Let's say out of 20 data, so I need 5.25 data. 5.25, let's say this is the one. I plot something here. I drop something here. This particular value is my Q1. Similarly, 15.75. Okay, this is my 15.75. Drop it down here. This becomes my Q3. So Q3 and Q1 can directly be found out once I have my cumulative frequency curve with me. So these are the four mechanisms that are available. Interpolation is that Excel process which we have used, no? Which is find out the difference between the two. See, I require 15.75th element. The 15th element is 23. The 16th element is 32. So how do I find out 15.75th element? The mechanism of interpolation is nothing but you try to find out the value between 23 and 32, which is 75% of the distance away from here and 25% of the distance away from here. The simple way we are using that is 23 plus find out the difference between 32 and 23. 32 minus 23 multiplied by, we need 15.75. So take it by 0.75. This value, this process is called as interpolation, where we are trying to find, we only have 15th value and 16th value, but I require 15.75th value. Right? So I am trying to, so for me it will be somewhere in between these two, because I have already arranged them in the ascending order. The 15.75th value will be somewhere between these two. But what exactly is it? We are using the process of interpolation itself. The 75, it's not exactly in the middle. It is 75% away from 23 because it is 0.75. 75% away from 23, 25% away from 32. So for that we are saying, okay, 23 plus whatever is the distance, multiply it by 0.75. So this gives me like 9 into 0.75, which is 6.75. 6.75 plus 23, which is making it 29.75, is the 15.75th element. This process we are calling as interpolation. Whenever we don't have a particular value, we are trying to fit that value by knowing the value before it and the value after it. That process of fitting the value using a proportionate distance is what we call as the interpolation process. Right? So these four methods, if we are comfortable, and most of the times what I have seen is sample standard deviation is the typical question. Right? Because the most commonly used also, even in the very advanced stages also, if it comes to first moment, mean is used. Second moment, variance, and thus the standard deviation is typically used. So though there are various methods of dispersion available, the most common one is standard deviation, and even your calculators are comfortable in calculating that standard deviations quite comfortably. So that you should not actually waste time in terms of trying to compute your standard deviation using the difference, square. It will eat up a lot of time.